So we're still talking about probabilistic context-free grammars. We said kind of everything that's important to say, but I'd like to rehash it since we did it kind of in a rush. And especially, I would like to create a nice, strong one-to-one mapping or correlation or analogy with hidden Markov models. So I'll try to do it side by side. We'll start with the graphical representation. So HMM will be here, and PCFG will be here. The graphical representation is something like this. Whereas here, I'll write it sideways. I wrote it top to bottom before, but I'm trying to take a similar amount of space. So it'll be sentence here, and it goes into noun phrase and verb phrase. And the noun phrase goes into determiner and noun, and the verb phrase goes into verb and noun phrase, da 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 da, and this ends in the. And this will be boy, and this will be kissed, etc. So we have a whole tree here, and this here will be the boy kissed, and this would be maybe a determiner, a noun, and a verb past. So here it'll be also VBD. So here's an example of a sentence that can be modeled by a left to right HMM. I'm sorry, by an HMM, not the left to right. By an HMM as a left to right set of words, or it can be modeled by a tree. There are probabilities here and here, right? In fact, I'll write what they are. These are A's. These are B's. Whereas here, it's one and the same. What do we call this? Phi's. And so forth. The requirement, the normalization requirements is that for a given state, all the probabilities that transition out of the state must sum to 1, and all the symbols that come out of that state must sum to 1. These are the transitions, these are the emissions. Here, it's a combined thing. Given a particular node, particular non-terminal, all the productions out of that, whether they lead to two other non-terminals or to a single terminal, summed over all of those together must sum to 1. That's a definition of the model. Now, calculating the full likelihood, that means the probability of the observables and the hidden state sequence given the model, is easy. They're basically 2t multiplications. Because you take the Q sequence, which is written here, and you take the O sequence, which is written here, and you basically calculate the B times A times B times A times B times A, right? This long sequence, right? Takes 2 times T multiplications. Easy. What would be the equivalent here? With the probability of the full derivation. So I'll call it also O and Q, given the model. That means if you're given the fully annotated tree, and it's also easy. It's just a product of all the appropriate phis. Right? This, the one that splits, I'm sorry, I put them on the arrows, but they shouldn't be. I don't know. There's a particular phi that corresponds to S becoming NP-VP. So maybe I should put it like this particular split, and it sits here. Right, this is the phi of S becoming NP-VP. And there may be another phi of S becoming something else, maybe just a VP. So whatever it is, there's one for each one of them. But basically, if you're given the model, as you were given the model there, and you're given a fully annotated tree, you can just multiply the appropriate phi's, right? Easy. Now the harder problem, P of O, given the model. You're only given the observables, the surface form, the words in this case. And you ask, what is the probability of that given the model? This is, in principle, a sum over these kind of terms. To decide in what order to write them. Sum over all Q's, all hidden state sequences. Each one of them is easy, but there are exponentially many of them, right? Exponentially many. So a simple summation will not be computationally feasible. Instead, we do dynamic programming. Dynamic programming, where the dynamic programming, the recursion is over the position time. Recursing over t. T is the position in time. And this goes by the name the forward algorithm. Also known as the alpha table. Filling the alpha table. Okay? You remember all of that from HMM? Oops. What is the analogous thing in PCFGs? It's the same thing. It's the probability of the observed sequence, the sentence, conditioned on the model. And that is exactly the same thing. It's the sum of P of O and Q, where Q corresponds to the parse tree, the exact set of derivations that was used to derive it, given the model. And, not surprisingly, there are exponentially many. One could even argue that it's a larger exponent. The number of possible trees is maybe larger than the number of possible hidden sequences. The solution, in the same way, is a dynamic programming solution, where the recursion is now not on the position t, but on the length of the fragments that are accounted for. Recursing over call it j minus I, the size of j minus I, of the indices, the length of the fragment. This goes by the name of CYK algorithm / alpha beta calculation tables. The recursion here is a little bit more complicated. Here you can calculate the alpha table by itself. You don't need any beta. You could also calculate the beta by itself. You don't need any alpha. Alpha is basically recursing, going from t equals 0 and building alpha of times t plus 1 based on alpha of time t. And beta is going from the back to the front. You could do either one. Here, to fully fill the alpha and beta tables, there's a relationship between them. Alpha is expressed in terms of other alphas, but beta is expressed in terms of other betas and other alphas. So you first need to do the alpha table, and then you build the beta table from it. If you remember that, it uses this triangular table. It's all conditioned on some tentative value of the parameter. So that's the evaluation problem. Now we have the decoding problem. Find the hidden state sequence that maximizes over all possible hidden state sequences the posterior likelihood of that state sequence given that we observed something and given a tentative model. This is the same. Sometimes it's easier to look at it this way. This is the same as P of Q and O given the model. Of course, this is not the same as this. I moved the O from here to here. The value of this is not the same as the value of this, but the thing that maximizes this is the thing that maximizes this because they differ by P of O given the model, which is a constant with regard to all the different Q's. So the algorithm to do that, very similar to forward algorithm. It's called the Viterbi algorithm. Basically, it uses max instead of sum. If you replace this max with a sum, you basically get this, the forward algorithm. So forward and the decode problem and the evaluation problem both are solved with the same dynamic programming, with the same kind of recursion. Only one uses summation over all possibilities, the other one uses maximization over all possibilities. What is the decoding problem here? It's the same thing. It's find the tree. I called it Q earlier, but it's really the tree. So Q is T, the tree, the parse tree. Parse tree. And O is the word string. Word string. So maybe I should have replaced these with W and T, but hopefully you know that. So the Wiener tree is the one that maximizes over all possible trees the posterior likelihood of that tree given the observed word sequence in the model, which, using the same trick as we used over there, it's the argmax over all trees of T and the word given the model. And again, for any particular tree, this is easy to calculate. It's just a bunch of multiplications. But the problem is, how do you calculate it for all possible trees? There are way too many of them. And the answer is, again, dynamic programming. Then programming, just like CYK, except use max instead of sum. Do you see the strong analogy between the two? They're really kind of the same thing. They're just a different underlying graph structure. So this is the decoding problem. Now, a big caveat about the decoding problem for both cases. The solution of the decoding problem gives you the most likely hidden state sequence. In the case of HMM, it's the most likely sequence of parts of speech or whatever the hidden states are. In the case of context-free grammars, it's the most likely tree. But the most likely tree is not necessarily a likely tree. When there are so many trees, there could be 1,000,000 trees, one of them might be more likely than others, have a higher posterior, but its posterior probability might still be very small. So the example I like to give is if I buy 2 lottery tickets and every person in America buys 1 lottery ticket, I am the most likely winner. But that does not make me a likely winner. I have a chance of 2 out of 300 million and some, and every other person in America has a chance of 1 out of 300 million some. So I have a higher chance than anybody else to win, but it does not mean I have a high chance of winning. So if you use the decoder to give you a tree, just because it's the best tree that you can get, if you're only allowed to guess one tree, just because it's the tree that has the highest likelihood of being correct doesn't mean that you're likely to be correct. In fact, chances are you're extremely unlikely to be correct because there's so many possibilities. Same is true for the HMM. Most likely does not mean likely. Most likely is what we called MAP before, maximum posteriori. Given the model and given the observation, whatever we observed, posterior to that, after we took that into account, what is the most likely outcome? Okay. The third problem we have is the learning problem. I'll write here the parameter learning problem. On the HMM side, we have given just one big observation, find the one set of models, the winner model. I'm sorry, let me add one more thing. I say learn the parameters. The assumption here is that you are given the structure. Given the structure, but not the parameters. What does structure mean in HMMs? It means the number of states and possibly the topology of which state is connected to which other state. If you don't want to deal with which state is connected to which other state, assume they're all connected to each other, and then you're throwing the problem into the parameter learning stage to learn whether the parameter value should be, the transition should be 0 or not. So the connectivity of the states can be thought of as either part of structure learning or as part of parameter learning. But the number of states is clearly a structure problem. So given n, number of states, and an observable, find the set of parameters that maximizes over all possible parameter sets the probability of this observable given the parameter. This is basically solve the maximum likelihood problem. Find the maximum likelihood set of parameters. What would it be here? Given the context-free grammar, that's the structure here, the set of productions. And again, you could say any production is legal. Any non-terminal can produce any word, and any non-terminal can produce any other 2 non-terminals. But some of these productions have probability 0. You could do that, but that would make life very, very hard because the number of productions would be way too large. In the real world, the linguistic intuition or your linguist friend will give you a context-free grammar, a finite and reasonable size set of productions. So given the CFG productions and the observables, which would be W. I'll put a bar because that means multiple sentences. We want to calculate the winning set of parameters, call it ML, call it ML here too, as the argmax over all parameters of the probability of this W given the parameters. Both of these cases are classic examples of wanting to learn a maximum likelihood from incomplete data. Right? That's the hallmark of EM. When you need the maximum likelihood, but the data is incomplete. What do we mean by the data is incomplete? It doesn't mean necessarily that literally there was data and we didn't get it. It could be that there was other data, like the annotation, somehow we lost them. But it could also mean that the way the likelihood function is written as a function of the observed data is complicated because it depends on intermediate decisions that are not visible to us. In this case, we have a very clear intuition in both cases of what that intermediate steps are. Here, it's what the hidden state sequence or maybe parts of speech are. Here, it's what tree structure is. But we don't know what the tree is. There could be many of them. If we don't know what the hidden state sequence is, there could be many of those too. In both cases, we have the same problems. We're going to use EM to iteratively improve on our estimation. And in both cases, we are only guaranteed that the iteration of EM will improve the likelihood from step to step, certainly not decrease it. If the likelihood function is bounded, we're guaranteed to converge. Is the likelihood function bounded in these two cases? Is the likelihood function of probabilistic context-free grammar bounded? When can likelihood functions be unbounded? Likelihood is probability, right? Or not? I'm sorry?
It is bounded.
It is bounded. Why?
Because the maximum value will be 1.
Because the maximum value would be 1. It's a product of probabilities, and each probability is between 0 and 1. This is certainly true here, because the likelihood of any component is easy. It's just a product of the derivation rules. Each derivation rule has a probability between 0 and 1. A product of numbers between 0 and 1 is guaranteed to be less than 1. Even if you sum over all possible Q's, you can still show that it's all well under 1. In fact, without even summing, just saying what is the probability that the model will produce these observables, it's a distribution over all observables, and if the observables, each one of them is a discrete sentence, each one has to have a probability less than 1, much less than 1. There are many, many sentences that could be produced, right? If you look at the model as a producer of sentences, every sentence has probability of clearly less than 1 of being produced. So here it's not a problem. When can likelihood be unbounded?
When you are estimating the variance.
Right, when the variance is not bounded away from 0. But I'm looking for a more general answer, and that is when the likelihood is a probability density rather than a probability. Right? Probability means over a discrete space, every item has some probability value between 0 and 1, and they all sum to 1. Probability density measures something a little different. It measures the density of the probability, which could be unbounded. You should have known that. The fact that you're kind of giving me that blank stare is not good. In a probability density function, here's a very big Gaussian. Let's say this is the origin. Here's the mean of that Gaussian. Here's the standard deviation of that Gaussian. 1 could be here, and 2 could be here, and this could be very high. Why? Because what's important is that the area here sum to 1. The area has to integrate to 1, but it doesn't put any limit on the height of any particular position. Right? If you can make it very, very narrow, you can make the area integrate to 1 and still be arbitrarily high. So likelihood is not bounded if it is, it's not a priori bounded if it is, or not necessarily bounded, if it is a density function. We don't have density functions in context-free grammars. We do have them in HMMs, possibly. When HMM applied to language, to words, again, it's a distribution, it's a standard probability distribution, then it is bounded. But if the observables from the HMM come from a continuous domain, such as acoustics in the case of speech recognition, then it might be unbounded. In our examples, both of them are bounded. L is bounded. Bounded. And therefore, EM will converge to a local maximum So that's what the algorithm guarantees. Now, how does the algorithm operate? It operates exactly the same in both cases. Here it is called the forward-backward algorithm. Also known as the Baum-Welsh algorithm. Here it is known as the inside-outside algorithm. By the way, the terms forward, backward, and inside, outside correspond to the alphas and betas. So if we go back to the this is decoding, no. We want the forward problem. Alpha. Alpha is forward probabilities, and the betas are the backward probabilities. Here, alphas are the inside probabilities, and the betas are the outside probabilities. How does the forward-backward algorithm work? You initialize the parameters, lambdas of iteration 0, which consists of the transition of iteration 0 and the emissions of iteration 0. I put double bars to remind you that these are matrices. And then, in the general step, I calculate alphas and betas from the existing model, lambda of iteration L, and the observables. I then calculate those psi t of I of ij, which, to remind you, are the expectations of those z tij's of the indicator variables that say that have a value of 1 if at time t the system transitioned from state I to state j, and value of 0 otherwise. So I basically use the alphas and betas to calculate these expectations. So I write it conditioned on the model and the observables. I'll calculate that from the alphas and betas. And then the third step is I re-estimate the A's and B's. And call that the lambda of iteration L plus 1. This is all old, not new for you. All right, what do I do in the inside-outside algorithm? Okay, and then I come back from here back to here. This is my iteration. These two together are the E step. This is the M step. Here I do the same thing. I initialize my thetas. Then I calculate the alphas and betas. Exactly the same as here, except the formula is different. But I calculate the inside and outside probabilities, fill the table from the current model of iteration L and the observables, which in our case are the W's. Then I calculate, I don't know if they call them psi there. I'll just call them expectation of Z for each transition. The expected number of times that this transition occurred in that derivation. And then I re-estimate again, this is conditioned on the current model and the observations from the alphas and betas. And now I re-estimate the lambda L plus 1, which basically means all the phi probabilities from all these things. You could almost write the exact same code. I mean, if you write object-oriented programming, a lot of the code will be the same, and then the implementation of what it means, the recursion of the alpha and the recursion of the beta would be different. And then the re-estimation formula would be different. It'll be a couple of lines. And if that's true for HMMs and PCFGs, it's probably true for other models that can be represented as graphical models. So you can imagine writing code that is much more general, that is given a graphical representation, and then does EM for it. And indeed, you can do learning of parameters in graphical models using EM.
Can it be any graphical models, or should it be tweaked like? Should it be a tweak? Because I thought that the algorithm was meant for the tweak.
I don't know. I don't know the exact theory of what limitations there are. Do you know?
I thought that was a tweak, but I'm not sure.
You mean for graphical models in general?
I mean,
It doesn't have to be. The general graphical model in general, EM can be applied to generate to estimating the parameters when there are hidden variables.
Of directed graphical models.
Of the what?
Of directed graphical models.
Yes.
Yeah, undirected is a different story.
Yeah.
Undirected is a random field. Okay. Okay, that was, so we went through the problems in order of difficulty. You know, evaluation, decoding, learning of parameters. Now we can talk about learning of structure. The structure learning problem. Not surprisingly, it's even harder than the parameter learning problem. The parameter learning problem, we have kind of a solution. It gives us a local maximum, not a global maximum, but it's something. The structure learning problem, we can formulate it as an optimization problem But in general, it is very hard to come up with good solutions. Because you typically don't have nearly enough data to estimate the structure. But what would it look like in the HMM world? In the HMM world, it would be choosing the right or best n number of states, right? Maybe also choosing a topology, how they're connected. Well, how would we do that? Any suggestions? Suppose you're just given a lot of data. Choose the right number of states, assuming they're all fully connected. Remember, the parameter learning problem is you're given the data and you're given n. Go ahead.
So you try for different number of states and a fully connected topology and see which sort of topology maximizes the probability.
Right. So a natural thing to do is, since n is just a single integer, just try all the different, try a HMM. Well, HMM with one state is not really an HMM, but 2 states, 3 states, 4 states, 5 states, try all possibilities. Try all possible values, number of states. 2, 3, 4. And then how do you choose among them? What does try mean? Sorry, go ahead. Yeah, you can maximize the likelihood of the training data, so you can build the best model you can with each number, with each one. So we'll call it the parameters of the model with n equals 1, or maximum likelihood when n equals 1. I'm sorry, 2. Start with 2. Maximum likelihood when n equals 3, all the way to the maximum likelihood estimate of based on the same data when n equals 100. Let's say you stop at 100. Now,
you want to validate it against the holdout set to make sure you're not.
okay, so that would be one way, is to leave some data out and then do what?
Let's say 1%.
Then calculate the likelihood of the held out data under each one of these models. Okay? Okay. So let's look at the likelihood. So we broke the data into O consists of O train and O test. Right, we separate them into 2 parts. Let's look at the likelihood of O train given the model with parameter 2, with 2 states, with n equals 2, all the way to the likelihood of O train given the model with n equals 100. And let's compare it to the likelihood of O given O of the test set given the same model, n equals 2. The likelihood of O test set given n equals 100. So we have a series of 99 numbers here and 99 numbers here. What can you say about these numbers? You were suggesting that we will look at the likelihood of test data and what? Choose the model that has the highest.
I was thinking either the highest or maybe when the rate of improvement starts to slow down.
Are you assuming it'll improve?
Yeah. Yes.
Which one, this or this?
Well, you can't really say because parameters is only guaranteed to give you a local maximum, and the optimization space based on the number of parameters can be arbitrarily complex, and you can get stuck in.
That's a good point. That's a good point. What were you saying?
So I think on the training side, we're definitely,
Yeah, increase. So you're both correct in the following sense that in general, on the training data, because these form a hierarchical set of models, namely that every HMM of 2 states is a special case of an HMM of 3 states, which is a special case of HMM of 4 states. So these are progressively richer models. They are a superset. Then in principle, the best possible solution here would give you at least as good a solution as the best possible solution here. So in principle, in terms of the absolute maximum, the global maximum, these numbers would have to grow. In practice, because we're not guaranteed to find the global maximum, it really depends on what we start with. But one thing you could do is train the best model you can here, and then use that as the initial condition for training the best model here. And then you're guaranteed to not get any worse. So in practice, they will grow. And even the equality sign is probably, in practice, not justified. It's really going to grow and get better. But what's going to happen to the likelihoods here? They're not guaranteed to get better. So this is a more objective measure of the fitness of this model. So they might reach a maximum somewhere in the middle, which would be our answer. So that would be one way of deriving the answer, would be with an approach like that. This process is called model selection. When you have a set of models, when you're trying to choose among them, often it is a discrete set. It depends on the integer variable. Sometimes it could be continuous, depend on a single variable. But especially in cases where it's a hierarchy, where this model is a strict subset of this model, you can do that. You can do other things with its hierarchy. There's a statistical theory that says that as you add degrees of freedom, you expect the likelihood function to improve by a certain rate. The certain rate has to do with the log likelihood ratio is twice the number of degrees of freedom, something like that. I don't remember the exact number. Is Lawrence here? Lawrence is not here. He would have been able to tell us the exact formula. But in general, you can think of the added parameters that you add as added degrees of freedom that have to justify themselves by a certain amount of improvement. So this is a way of weighing complexity versus goodness of fit. So trade-off of model complexity versus goodness of fit of the model to the data. One way of measuring model complexity is number of parameters. One way of measuring goodness of fit is likelihood, the likelihood function. So as you go over all these possibilities, you denote for each one of them how many parameters it has, what is the likelihood, and then as you decide to move from n equals 5 to n equals 6, you say, the likelihood improved by this much, I paid this many more parameters. Was it worth it? That is an alternative to basing it on test data. There's one other way of viewing it, which is very similar. In the Bayesian framework, you don't think about number of parameters, but you think about putting a prior over the models. So what you're going to compare is the log of the prior over the model. That plays the role of the complexity, or the number of parameters, to the log of the likelihood of the data given the model. And by compare, you want their sum to be minimized. If you think of the log of the prior and log of the likelihood, their sum is like the log of their product, right? Their sum is a log of the prior times the likelihood of the data given the model. And this is proportional to the posterior. So you can view model selection in a Bayesian framework as choosing the model that has the highest posterior. This also goes by the name minimum description length principle, MDL principle. It's the minimum length measured in bits of the number of bits it takes to describe the model, which is usually proportional to the number of parameters you have in the model, and the number of bits it takes to describe the data conditioned on knowing the model. And the idea here is that the better the data fits the model, the fewer bits you need to describe the deviations. So this is a standard part of machine learning. I don't know if you've seen it before. How many of you have heard MDL before? Some, okay. You'll see it in machine learning, but I think one of the nicest way, best ways to understand it is through the Bayesian framework. It is really a map, maximum a posteriori. If you identify the complexity, if you're saying that more complex models are a priori less likely, less complex models are a priori more likely. So the likelihood of the prior is proportional to the complexity. And the goodness of fit can be measured by the log likelihood. The better the fit, the higher the log likelihood. Okay, so that's the general idea of model selection and structure learning. How does it apply? We talked about how it applies in the case of HMMs. Now, in the case of context-free grammars, it's a lot harder. Because the only thing we had to choose here was a single number, n. How many parameters? I'm sorry, how many states? But the structure in a PCFG is a full CFG, a full context-free grammar, of which there could be a gazillion, exponentially many. So how are we going to choose a context-free grammar? Well, one answer is just go to a linguist and lock them up in a room and ask them to not come out until they come up with one. You know the quality you're going to get, right? But really, one method is just to rely on linguistic considerations. You cannot afford to go over all possible CFGs. There are just way too many of them. But what you can do is a greedy search. You can start with something your friend the linguist gave you and consider making a change to it. For example, consider adding a production or taking away a production. If the grammar has 1,000 productions in it, which is reasonable, then taking away a production, there's just 1,000 possibilities what to take away. Adding a production, there are more possibilities, but it's also a finite number. Unlike, it's a manageable number, maybe in the thousands, maybe in the hundreds of thousands, but it could potentially manageable. And then, when you consider that incremental step, you can now look at how best you can train the before model, use the inside-outside algorithm to train the before model, propose the change, the addition or subtraction or change of a production, and train the after model. Look at the likelihood of the two. If the likelihood of the after is higher, maybe you switch to the after. So you do a greedy search in the space. So now, again, you're going to be stuck at the local maximum, but this time it's going to be a local maximum in structure space, not in the space of parameters. And you can think, if you have all the computation in the world, you can think of all sorts of tricks, like you can do conditional moving, like Gibbs algorithm, if you remember our discussion last time, where you look at the likelihood of this, you look at the likelihood of that, and you don't necessarily change from here to here, but you change with probability that depends on how much of an improvement this is. So you allow yourself to transition even when it's not an improvement, even when it's a step down, because that might allow you to escape from a local maximum. So you can do a gazillion things. You can, I mean, it's really wide open, but the point is for each one of them, you need to retrain the candidate grammar. Now, granted, the candidate grammar will probably have parameters very similar to the parameters of the previous grammar, because you only changed one production, so the maximum likelihood solution over the parameters might be very similar. So if you start from these same parameters, maybe you only need 1 or 2 iterations. Or maybe you can even solve it analytically without iterations. I don't know. But still, it's a lot of computation. That would be a search just to find a structure that gives you the highest likelihood. But you have to be careful with that, because it might degenerate into a huge number of preterminals. You need to somehow constrain the complexity of that model. So you can introduce a prior over the structures, over the context-free grammars, maybe proportional to the number of transitions. Questions? Okay, so let's move on. Let us talk today about semantic modeling. So the closest we got to real language was modeling syntax with a context-free grammar. You know, before that, we didn't even try to think of language as a real language. We just thought about it as this sequence of symbols. But context-free grammars allow us to capture the basic intuition of syntax. Can we do something similar for semantics? Can we capture, even in an incomplete and suboptimal way, but somehow capture the idea that language is about stuff, and that some sentences may be more semantically coherent than others? So a sentence can be syntactically coherent in that it's parsable using a context-free grammar, and yet it may be semantically completely incomprehensible or doesn't make sense, not coherent. The classic example that Chomsky gave is colorless green ideas sleep furiously. You all heard that before? Okay. It is a adjective, noun, verb, adverb, right? There's at least one parse that is perfectly fine, but it just totally doesn't make sense. So how can we capture that in a model? Well, one way to capture it is to ignore the syntactic structure and to look only at the words, and specifically at the content words, as conveying some part of the meaning of the rough semantics of the sentence. So look at what content words are in the sentence. So take a sentence or a document or a paragraph, throw out the function words like of, at, in, the, so forth. Keep only the content words, which are typically nouns, to some extent verbs, and maybe to some extent adjectives and adverbs. We'll keep all of them. And look at them as a bag, not in a particular order necessarily. Of course, you lose a lot of semantics. Man bites dog is not the same as dog bites man. But you got the general idea that there's biting going on and who the involved characters are. So how would we capture that? I will try to do it in the context of whole documents. Because in whole documents, you're not trying to capture one particular logical statement, but you're trying to capture what the document is about. That's extremely useful in information retrieval, right? As well as in other areas. So the first thing you might want to do is take all of your documents in your collection and represent them all as bags of words. In fact, you might want for every document to represent it as the set of content words that are in it, perhaps each one with how many times it occurred. So that would be a count of, in document J, of word I. You can put it in a big matrix. The matrix might contain words from word 1. Let's see, which one do I want to put in the column, and which one do I want to put? Word would be the first index, and therefore it would be the column. Okay. So here would be my words from word 1 to word V, where V is the size of the vocabulary. And keep in mind that V is about 10 to the 6. I'm sorry, 10 to the 5. We typically work, I've mentioned many times, with vocabularies of about 100,000 words. Could be 200,000 or 300,000. Could be even 1 million, but this is the order of magnitude. Let me change again. Not call it V, let me call it N, because I'm going to do some linear algebra soon, and we're all used to N in linear algebra. And here, I'm going to write all the documents in my collection, call them D1 through DM. M documents. M equals, let's say, order of 10 to the 6 documents. So the important thing to note is this matrix is not necessarily square. In fact, it won't be square. It will be rectangle. Also, typically, it would have more documents than words, but not necessarily. I may list all the words here, or I may exclude function words like of, the, and whatever, if I think that they're not informative. It turns out in the real world they are somewhat informative, so I might choose to keep them. And my ij entry, so I'll write it as ij, might be the count of how many times each word occurred in each document. Or I might want to improve on that by trying to choose a weight that better reflects the informativeness of the occurrence of that word in that document. How much does that word tell me about the semantics of the document? If I do that, I'm no longer worried about including words like of and the and on, because they might end up, if I do my job right, I might get a very low weight. So I will call it, instead of C, I realize I'm changing things fast, it's hard for you to change. I'll call it W for weight. And there are many ways you can choose this weight. One particularly frequent method, or commonly used method, comes from information retrieval. And it's called TF-IDF. How many of you know what TF-IDF is? Okay, not everybody, so we should go over that. This stands for term frequency inverse document frequency. It is a product of two terms, so it should be called TF times IDF. The first is a function of the count of how many times, by term we mean word. It's another word for word. Another term for word is term. It'll be a function of how many times word I occurred in document J. It could be just a count, but I'd rather make it a function of the count in a way that I'll explain later. Document frequency is actually not the frequency of documents. It is the frequency of the fraction of the documents in which the word occurs. Okay, so it would be 1 over, so this is the inverse part, 1 over number of documents that contain word I. I use W here. just call it word I. And it won't be 1 here, it'll be m, the number of documents. So this tries to capture how specific is the word to particular documents as opposed to occurring in all documents. So the word the is so non-specific, it occurs in all documents. And therefore, the number of documents that contain the word the would be m, right? All of them. And m over m would be 1. I don't want to multiply by 1. I want to make it completely non-informative, so I will take the log of this. Log of m over number of documents containing the word I. Whereas, so for the case of the, this would be m over m, which is 1. Log of 1 would be 0. This multiplies it by 0. That means it doesn't matter how many times the occurred in the current document. Since it occurs in all documents, I'm not going to count it at all. It's not going to affect my weight. Imagine a word that occurs in exactly one document. That word is highly indicative of the topic. It only occurs in that particular topic, the super subtopic that this document is about, that no other document in the collection is about. In which case, we'll have 1 here, and we'll have the largest possible value, which is log of m. So this thing varies between 0 and log of m. So this captures something about the word itself, about the informative of the word. It depends only on the word I. It does not depend on the document. It's the same value for all documents, for any particular given word. This depends on the number of times the word occurs in this particular document. And the question is, how should the dependence be? If a word occurred once, that's somewhat informative. Let's say an informative word, a word that does not occur in all documents, occurred once in a new document, it tells you something about the topic. If it occurs a second time, it gives you more information, maybe more confidence. It's not a noise, it's not a random case. But it doesn't give you as much information as the first time it occurred. Certainly, if it occurred 6 times or 7 times, there's not a big difference, right? So there are several ways you can think about it. You can think about the fact that any subsequent occurrence gives you less information. So this is kind of a diminishing returns, or diminishing addition. Or you can think about it that words tend to be bursty. Once they occur, the probability of occurring again is very large, and your surprise in seeing them the next time is not as high, so it doesn't give you enough information. It's all the same thing. What comes to mind is something that looks like this, the amount of information you get. Or if you talk about the cumulative value of it, it would look like this. So the first occurrence would bring you from 0 to 1, would bring you to here. The second occurrence would bring you just a little bit more, just to here. And the difference between the 7th and the 8th occurrence is going to be almost negligible. Right? So this function is nicely approximated with the log. In fact, you don't want to be at 0 because this is negative infinity, but you can be here, a log that's shifted, so it'll be log of 1 plus the count. So this is an argument for using here log of 1 plus count ij. So if the word did not occur at all, so log of 1 is 0. Does not contribute to the weight. If it occurred once, it's log of 2. If it occurs twice, it's a larger number. But as it occurs 7 or 8 or 9 or 10 or 11 times, every time the addition is smaller and smaller. This is not the only way to do it. And there are theoretical arguments for this and against this. Some people think of it as ad hoc. Some people try to derive it from some, statistical principles, some assumptions. But it is a very common function to use here. There are people here who work in IR, so they know better than I do what the current state of the art is. What
Actually,
the-
there are several ways to define it.
Okay.
There are, like in classic BM25, it actually kind of linear dependence, and the term frequency is also normalized by the length of the document, but it's not. Kind of-
Right.
Yeah, but there are like four common, like most common ways.
Right. I forgot. This is.
Space moving and yeah.
Thank you. I forgot an important point. Some documents are longer than others. And the significance of a word occurring in a short document is arguably more than the significance of a word occurring in a long document. If a document is 50 times larger than most other documents, of course it's going to contain all sorts of words, right? So a better variation would be to take this count and divide it by the length of this document, document J. So that's one of the variations that are important to mention. And there are many other. There are even people who optimize a non-parametric, numerical match. Yes?
I think that, well, in my opinion, that some of them, some of the TF-IDF variations can be interpreted as a cross-entropy distribution of, like global term distribution and local term distribution in each document.
Uh-huh.
But it's not literally this way, like for all the, some look more like cross-entropy,
Uh-huh.
some less.
Okay. A lot of work on this. Some of it principled, some of it ad hoc, just whatever works better for retrieval. That's not the focus of what I want to say. This is just our starting point. So imagine that you chose one of these formulas, maybe a TF-IDF one, maybe a variation, maybe exactly this one, and you filled your table. Now what do you have now? Now you have a matrix of words by documents, of co-occurrences weighted by their significance, or what you think is their significance. Now what can you do with it? The answer is not that much by itself until you realize that the space in which you work, which is a huge space of n by m, number of words by number of documents, which is 100,000 by 1,000,000, or these days it's much more than 1,000,000 documents, that space is not really as high dimensional as it appears. I mean, if you look at this matrix of n by m, that's 10 to the 11 at least parameters. But you might have in mind the kind of semantics, the kind of topics that you're thinking of modeling may come from a much more limited space. In fact, there may be just 100 different topics. Sports and politics and science and local events and education and whatever. And even each one of them could be sports, could be basketball and football and softball and what have you. Could be some variation. There could be a hierarchy of topics. But you might have in mind 100, 200, 500, 1,000, not 10 to the 11 different possibilities. So our goal now is to take this matrix and try to extract from it a much lower dimensional space, which is a space of topics. And one way to think about it is to say that somewhere in this document, in this matrix, hides a small number of combinations of words. So if you think about the topics, a topic being sports, then there may be several thousand words in the vocabulary that are sports related, and they tend to show up whenever there's a sports document. So they co-vary. When one of them shows up, another one tends to show up as well, or all of them tend to show up together. And another topic would have a different set of words, some of which might be overlapping. Like mouse might show up in articles about hardware and articles about, home sanitation and articles about nature, right? So some of the words, you wish it were that simple that every word clearly said what topic it is, but it isn't. They overlap. But what you're after is not the occurrences of individual words, but the occurrences of subsets of words together. The problem is that the number of possible subsets of words is huge, right? You're not going to try all possible subsets. You can't. You don't have enough data for that. If you have 100,000 words, the number of possible subsets is 2 to the 100,000. We've been through that. So you need a way of deriving those subsets of words from the matrix. You need a way of discovering subsets of words that tend to vary together. And furthermore, They don't all have to move exactly together. Some of them might be much more indicative than others, but they all point in a certain direction. So imagine a linear combination of words. You say 30 times the word ball, and 70 times the word referee, and 22 times the word, some linear combination of these words that together define what it means to be sports. So you can think about it as regression over the words, or over these terms, these W's for the words, defined terms. But again, how do you come up with those? The other way of looking at it is through the collection of documents, not the collection of words. You can take the collection of documents and try to break them into categories, into topics, sports, politics, just by reading them. And that's easier to do. If you have in advance a set of topics in mind, you can decide to classify each document according to its topic. There may be some disagreement between people sometimes, but for the most part you would agree. But what if you don't have in advance a set of topics? If you have in advance a set of topics, you're restricting yourself to a division of the semantic space that you had the preconceived notion of. But suppose you don't have a preconceived notion, or you don't want to trust it. You want to find the best possible dimensions of the discussion, rather than coming up with your own ideas of what the dimensions are. Then you have this chicken and egg problem of documents and words. If you had the right division of the documents, you could use it to construct the right division of words. If you had the right division of words, you can construct the division of documents. I shouldn't say division of words because it's not a hard division. It's a soft division, but nonetheless. What we're going to do is try to solve this problem through linear algebra. And obviously we only have 2 minutes to discuss it, so we'll continue it next time. But we're going to use singular value decomposition. And since we don't have time to do all of that and the topic we wanted to discuss next time, I'm going to ask you to go on Wikipedia or any of your textbooks and read up a little bit about SVD, stands for SVD, about the properties of SVD, and then I will be able to just give you the hand-waving part of what SVD does for us. So we're going to take this matrix, call it the X matrix, it's this whole thing, and we're going to decompose it to a product of 3 matrices using SVD. So look up SVD and then also read the paper that was in your reading list about the use of SVD. By the way, this was originally invented, SVD is an old mathematical technique. The use of SVD for text was invented by the IR community, by a bunch of people at Bellcore. It goes by the name latent semantic analysis. Latent semantic analysis with the letters LSA. So LSA is basically SVD applied to Word document co-occurrences. All right, thank you. We'll see you next time.